And so it turned out that there was no evidence. So the moments in the sun had gone. And then, most people know I probably devoted most of my life to baryonic dark matter, and I've gone through, I spent phases of about 5 years each studying various black hole dark matter candidates, baryonic dark matter candidates, round dwarfs, red dwarfs, white dwarfs, black holes, BMOs, SMOs. But I mean, at that stage, it was a pretty sad period for machos. There were things like papers being written, the death of stellar baryonic dark matter, RIP, the macho era. So, and people like me who devoted our lives to it, was a bit depressing. But then I changed my philosophy. Because then the question is, what is dead? The point is, something can be important even if it doesn't have an identity. By now, we have thought, it wasn't likely that most of the dark matter is going to be in these realms, but they can still be important. I mean, arguably the most important thing, even on Earth, are people in this audience, like the people, for example. Gibbon's mass is very unimportant. So the idea that something is only important if it's cosmologically significant and density is really a myth. These things can be interesting even if their density is low. And of course, nowhere more there is that the supermassive black holes and galactic nuclei. We know those don't only have a tiny part of the cosmological bit, but they're incredibly important. So, but then nice things started to happen. First of all, more sophisticated calculations started to show that the first stars in the universe really would be massive. I mean, in the VMO range. Of course, there was some controversy, but these were more detailed numerical calculations. And I'm not going to go through the papers in detail. People started looking at sort of the ways in which the VMO black holes, or by now they were called intermediate mass black holes, might form. This is sort of rather like the diagrams that people like Mitch Begelman and Martin will draw for making supermassive black holes, but the equivalent ones for intermediate mass black holes. And so really, at this point, things are on the up again. And also people like Stan Woodsey, etc., were realizing that these VMO explosions could be very important, both in enriching the gamma, in chemical enrichment, and also in making gamma ray bursts. Some of the models of gamma ray bursts involve these very massive stars as well. So then really, a lot of interest started focusing on these intermediate black holes. Influential paper by McDowell and Rees, arguing that the first objects to form would be the intermediate mass black holes in million halos at about a ratio of 20. This, of course, in those days, the CDM, but soon to become the Lambda CDM model, which everybody now accepts. And it was realized that it was fairly natural in those scenarios for these black holes to form. They could have a density comparable to the black holes in the supermassive black holes in the nuclei. They would tend to fall into the nucleus and get captured by the supermassive black holes, and they would generate upluminous X-ray sources and gravitational waves. So this is quite an exciting period. Another interesting paper a year later talking about these sorts of processes in more detail, by Schneider et al. Then a paper by Joe Silk and others, considering actually how much of the supermassive black holes in the galactic nuclei could be associated with this process. So it's the link between the very massive black holes and the supermassive black holes which is so interesting. People started realizing that the light from these stars may have been detected. I said that there was that background radiation observations excluded having most of the mass of dark matter in these objects, but there would still be some associated with the first generation of stars, which used the initial enrichment. It was realized that you could have, around each intermediate mass black hole, you could have a little mini halo of dark matter which would generate annihilation, and that would be one of the key signatures. That was a paper by Zhao and Silk, and a more detailed analysis later on. So at this stage, you can see popularity here is measured by how many papers people are writing on consultant and help very influential people, like Joe, are working on the subject. So at this stage, it's really exciting. And that really, that's sort of almost the story. But I want to say, just being on the personal side a little bit more, my greatest collaboration with Dick was in 2003, because Dick, besides being a great collaborator, is one of my best friends. Dick was the best man in my wedding. So I hope it's not too self-indulgent to show that picture. Incidentally, Dick, you know, nothing goes quite according to plan. And just before we got married at Trinity College Chapel, just before the wedding, we had a little dress rehearsal, you know, with the ring, and this is literally just 5 minutes, 10 minutes before. And I said, Dick, can we have the ring? And he couldn't find it. And what had happened was, it turned out I'd hired a morning suit for Dick from Moss, and there was a hole in the pocket, forward through the hole. Now, I don't know if you've ever tried to get a hole, something out through a hole in the pocket. Very difficult. And so, and Dick was bringing out everything which previous people had. Cigarette lighters. Finally, we got it. But the wedding went ahead as planned. The point of this story is that whenever Dick's involved, there's always complications, but he always sorts it out in the end. Now, I wanted to actually, this is too detailed, so I'm not going to go through this. Let me just say, do we believe now that these intermediate black holes and very massive stars exist? And I would say the evidence for them is now very good. Here is a paper which just came out in 2010 by Begelman et al. I think, you know, clear detection of a pair instability supernova. And I won't go through the details. Let me just say that it really does have all the characteristics which would be expected of one of these pair instability supernova. So although they're rare, they do exist. Let me not go through the details. Let me just say that it fits, and I think most people are quite convinced by that. Probably the most the best evidence for intermediate mass black holes probably comes from the ultra-luminous X-ray sources. There are arguments that they could be black holes in the mass range 100 to 100,000, because if they're increasing again to the limit, they have to be that massive. There are various particular candidates, which, for example, there's a candidate for 200 to 500 solar mass black hole source. There's M74. That seems to be a 10,000 solar mass black hole. I mean, obviously people can argue about it, but not now. There's another one which is 2,000 solar masses. There's another object, all of these are detected by the X-ray satellites, 12,000 to 34,000. That's in the 82. So I think these things exist. I'm not now joking, I think they really do. Also, that's a particularly famous one in the spiral galaxy, ESO 24349. Let's just say the evidence is very good. And then the other thing that makes me think these exist are in the centers of globular clusters. There are reasons to believe that there could be intermediate mass black holes in the centers of globular clusters. If you simply extrapolate the famous mass loss in dispersion relationship to supermassive black holes, the small masses, you would end up predicting that there will be intermediate mass black holes in the centers of globular clusters. And there is some evidence for this. Yes, just finishing 1 minute ago, Peter. In particular, there's the famous case of Omega Centaurus, where people think there's a black hole of 40,000 solar masses from the dynamic observations. Well, I don't want to go into this anymore. I just want to add this final step, therefore. This is the accumulating evidence. This has gone off the graph. This has gone off the graph. The popularity has basically gone off the graph. So right now, I wanted to end the note on a high, the talk on a high note. I really do think these VMOs that we used before, I'm afraid we're going to go to the normal convention now. I think this turns out to be very important. And it's been, just as evidence of that, there was a whole meeting devoted to intermediate black holes only last year. You can go to the website if you want more details. John Wise gave a, was it John? John Wise gave a talk on it just about their reorganization text. Anyway, just to finish with Dick, what you might not realize is Dick is a very cultured person. Whenever he comes to London, we always get together, and he always wants to go and see a play. So we always go to a play, and we always take a photograph outside the theatre of the people who are there. But now, then something started happening a few years ago. We were at a play, and in the middle of the play, his mobile phone goes off. And it turns out he's just won a prize. He's won the Hertzberg Prize, I think it was. Which was exciting. And then it happened again. We went to another play, and again the phone went off. And I don't think it was a Krieger, but it was one so many I forget that another one went off. Again, you got a prize. So every time Dick comes to London now, we go to a play, and right after the he's going to win another prize. Anyway, Dick, whatever, you've won many prizes, and I know you're going to win many more prizes. And I'd just like to end by saying very happy birthday today, Dick. You've lived for 2 billion seconds, and I hope the next billion seconds will be even more interesting. Thank you, Dick, for your attention.
Are there any questions? Okay, I guess that's the end of the session. We should thank the speakers again.
Just a quick reminder, there's coffee in one channel across behind the elders, and if you haven't mentioned it, you can
written a paper together, but we came closest to collaborating on the topic of feedback. So that's what I'm going to talk about. But I can't really talk about our almost collaboration on feedback without also having a flashback to the time when we shared a house in Berkeley, which Vernon's already told you about. This is 2311 Hearst, as it was seen by the Google Street View truck. In fact, there is a 3D version, and if I realized that Carlos had brought a load of 3D glasses, I might have shown that and started that. But anyway, the house is still there. It looks a little bit more faded than in Bernard's photo. Perhaps that's just changing imaging technology. And it indeed is known to us as the BBC house. But our collaboration on, or almost collaboration on feedback, didn't really quite get going here. It really started when Dick suddenly discovered or invented the concept of feedback on a street corner in Ashkelon, Israel on December 26, 1984. I realize it's Carlos feels he invented it, but there were the seeds there. This was right after the Texas Symposium in Jerusalem, and we spent more than a week, I think, driving around Israel. And I guess this was when we were on our way back from Eilat. I think we just climbed Masada, and we're heading up to Lake Tiberias, where we ended up partying with the UN troops. I am pretty sure that there are slides of this trip, but perhaps it's fortunate that after a morning in my basement I could not locate them, so you'll have to imagine what went on. We did have this tremendous intellectual atmosphere at 2311 Hearst. It was a real, I'm sorry. Let me just say, first of all, to set the stage, what we were trying to do when we talked about feedback was we were trying to determine the effect of this, large radio galaxies pumping out jets and energy into the intergalactic medium, on this, clusters of galaxies. And there's a picture of part of the Coma cluster with a couple of radio galaxies flying through it. And I'll say more of that in a couple of minutes. But the seeds for this were laid at in the intellectual hotbed of 2311 Hearst. You can see one of our intense discussions here, led by Bernard, before shaving. This place attracted, was really a scientific salon. It attracted some of the leading astrophysical minds of the times. There's Chris McKee, Mark Birkinshaw, and George Drogowski. And a couple of the speakers here, of course, George and Joe. And it was all presided over by Dick. We did have some discussions about jets. Jets were one of the hot topics in the early 80s, and I remember one night going out, I think, to Cafe Espresso up on Euclid and Hearst with Dick and having an extremely animated debate about jets for a long time. But it was only after about an hour that I realized that I was talking about jets from radio galaxies, and Dick was talking about quark jets from heavy ion collisions. But it didn't really matter much, and in fact it probably led to some creative results later on when we were in Israel. So suddenly on the street corner in Ashkelon, after driving for several hours, Dick said, let's do something on feedback, the effects of radio galaxies on clusters. I have no idea why we wanted to do this in 1984, but in fact, feedback did become something that became very important and much more sensible to think about by 2000. And I suspect that some of these early discussions influenced me much later on, even though we never actually wrote a paper about it. So that's what I'd like to talk about. It was realized that the well-developed theory, developing theory of galaxy formation based on cold dark matter, which had so many successes, really became much weaker when you tried to explain a lot of the baryonic physics that we can actually observe in great detail, such as the size, the masses of galaxies, and when they formed and what they look like. There's a problem with too much cooling going on, the overcooling problem. You end up with too many large galaxies and also too many small galaxies, and people began to realize that probably you needed something to quench the formation of so much baryonic structure, and feedback from the energy liberated by growing black holes turns out to be a very good candidate for that. So here is one example where there's a lot of indirect evidence for some kind of feedback, where if you try to model galaxy formation using gravity and hydrodynamics only, you get the wrong distribution of structures. Starbursts will only tackle some of the small-scale structure, but the large-scale structure really requires the kind of energy levels released by black holes. But this is still an indirect argument. There is, however, some direct arguments for feedback, and that comes primarily from the X-rays and all of the structures that we see being punched into the central regions of clusters of galaxies by active galaxies at the center. And perhaps the most famous example is the Perseus cluster and the bubbles found around NGC 1275, 3C84. Here's a Chandra image from the turn of the century, and we can compare this with radio observations and see that a very energetic plasma fills the hole. So that actually is, I think, the primary direct evidence that there actually is feedback going on these very large scales. We also see evidence of shocks being driven into the gas clusters by active galaxies. There are structures that really look like sound waves, but now we're getting into more nebulous territory of what these things really are and how they're dumping their energy into their surroundings. And there is some indirect evidence from the fact that some clusters exhibit cool cores, but nevertheless, the gas that's cooling in the cores of these clusters does not seem to be cooling all the way down. Something is stopping it in its tracks, and in this case, it seems that something is most likely the energy being input from the active galaxy in the center, which is always present. And so, for example, you see in the Centaurus cluster the temperature dropping by about a factor of 3 as you approach the center, but then leveling off. You see the gas starting to cool, and here are some of the lines that are carrying away the energy of the hot gas, but once you get down to a certain level of temperature, you stop seeing evidence of cooling. And so these are the lines that should be present if the gas continued to cool. So something is stopping the gas in clusters from cooling in its tracks. It's all happening in the central regions of clusters. Very likely that what's stopping the gas is something coming out of the central region, and the only thing pumping energy in there is a accreting black hole. So that's direct evidence for feedback. But all the other evidence that I know about is very indirect. Here's another piece of indirect evidence that I think is starting to get a little bit more shaky. There is, if you try to assemble clusters theoretically using hydrodynamics and cold dark matter, you can make a prediction of how much entropy the gas has. The observations indicate that there's an excess of entropy in clusters. It becomes more pronounced for smaller structures and groups, and so something seems to be adding extra energy to the clusters on fairly large scales, as well as the core cooling issue on small scales. Some scales around the size of the virial radius, but whether that's feedback from black holes, I think, is much less certain, because these clusters are sitting in a gigantic heat bath. There's an infinite amount, effectively an infinite amount of energy around, and it's quite possible that that energy is coming from somewhere else to give you this excess entropy. And for example, Roger Blanford's been arguing that it probably has to do with the primordial population of cosmic rays. So here, there's some evidence which you might explain in terms of feedback, but it's much less certain. But I think the area where it is the most uncertain is in the very surprising correlation between the masses of black holes in galaxies and the properties of the galaxies, which is now believed to be primarily tied to the velocity dispersion of the central regions of the galaxy sigma, and the correlation is very similar to the Faber-Jackson relation. The mass of the black hole goes like the fourth power of the velocity dispersion. Because of the fact of the Faber-Jackson relation, it's very hard to distinguish that from a strict proportionality between the black hole mass and the mass of the inner part of the galaxy. So in fact, it may well be a mass-mass correlation. And here's some data. It really does look like a good correlation when additional objects are added, and we don't really know what the origin of this correlation is. But most people think it's evidence of feedback. So what I'd like to talk about for the rest of my time is whether it really is likely to be evidence of feedback. Here's how feedback models for the M-sigma relation work. Black holes, when they absorb material, the material is usually believed to be rotating. It may well be turbulent. In order for that material to fall into the black hole, it has to give up some of its energy, which has a natural tendency to move outwards. And so the black hole growth pumps out energy. And the original ideas were that this energy impinging on the galaxy would actually inhibit the growth of the galaxy beyond a certain point. That idea was really put forward clearly by Silk and Rees in 1998. Unfortunately, it gave the wrong answer. It predicted that the mass of the black hole is proportional to sigma to the fifth. Whether or not that's possible, I'm actually not quite sure. Maybe Scott thinks you really can't distinguish. But most people think that, in fact, it has to be sigma to the fourth, and you can actually get that by modifying the argument so that instead of the galaxy absorbing all the energy, it just absorbs the momentum. And you can assume that there's a kind of shock blown out that cools down. And Fabian, King, and others made this argument. And this would really have to be a tremendously dramatic process. So this black hole, this little thing, smaller than the solar system, is growing in the center of the galaxy. It's putting out this wind, sending out some kind of a blast wave, like a stellar wind bubble, and that has to actually push away all the gas that's trying to form the galaxy. So this model has very dramatic consequences in either version. It means, first of all, that the black hole forms first or concurrently with the galaxy. The black hole growth is what limits the galaxy growth, so it's like the tail wagging the dog. Certainly not impossible. There's enough energy or momentum to do that. And it also means that the feedback would have to act over many kiloparsecs. Is that really necessary? Well, there are non-feedback models for black holes, and I don't want to go into these in too much detail. The one that I found most intriguing recently is one by a well-known Canadian theorist, Richard Larson, who basically extrapolated from popular models to explain the Faber-Jackson relation, which as far as I know is still not well understood, but it's often attributed to some kind of optical depth effect. And he pointed out, for example, that if you have a galaxy forming as some kind of an isothermal sphere, singular isothermal sphere, with the mass distribution like that, when the surface density exceeds about 8 solar masses per square parsec, it tends to become optically thick enough that you get a lot of molecular gas, and perhaps that is the condition that's required for a lot of stars to form, and that gives you the Faber-Jackson relation. Well, to get the M-sigma relation, he said, suppose the surface density exceeds 10 to the 4 solar masses per square parsec, which will happen if you go far enough in this distribution. That actually gives you an optical depth greater than 1, and we know that that gas clouds can't fragment if the optical depth is greater than 1. And so he proposed that that gives you the M-sigma relation. All the gas inside that point becomes the black hole. However, that argument actually doesn't hang together, because a gas cloud that massive, we're talking about millions or hundreds of millions of solar masses there, when it becomes self-gravitating, must be dominated by radiation pressure. It's a simple mass criterion. More than 100 solar masses coming together, radiation dominates. And so in fact, the fragmentation condition the condition to suppress fragmentation is not tau greater than 1, and you can extrapolate this from the famous paper by Lowe and Lindenbell in 1976. It's tau greater than C divided by sigma. And that gives you a black hole mass that's about 3 orders of magnitude too small. So in fact, that argument doesn't hang together, although maybe there's some other thing that tau greater than 1 does for you. So how else might the formation of a black hole suppress, either limit itself or suppress the galaxy from forming without relying on this enormous feedback operating over kiloparsecs? Well, I've been worrying about this, the formation of the first supermassive black holes for a number of years, and this is sort of a growing collaboration. Participants are listed down here. There's two schools of thought on how supermassive black holes form. One is that they grew originally from POP3 stars, which may have initially formed intermediate mass black holes, but to get to quasar-type masses, you have to have these intermediate mass black holes converging in galactic potentials and merging and also accreting a lot of matter. It's not really that easy to do. It would be much easier to form big black holes if you could do it all at once by huge infalls of gas which form black holes by direct collapse. And that becomes possible fairly late in the history of galaxy formation, not in the POP3 era of redshifts of 10, 30, 20, 30, 40, more like redshifts of 10, maybe 10 to 15, because by then you're accumulating large enough masses that the natural infall rate, which is sigma cubed over g, starts becoming really large. And as soon as you get infall rates larger than about a solar mass per year, you have a chance of forming black holes by direct collapse. There's a lot of controversy about whether this is a realistic thing to even consider. I mean, look, this is huge. For galaxy-type potentials, you're talking about 1,000 solar masses per year. Does that ever happen? I mean, this is gas that's able to cool down when it's still out at a kiloparsec. You might argue that it fragments, and that's the complaint I usually get. Well, it's not really clear how important fragmentation is, because the gas is never really forming a hydrostatic cloud. The way to think about this, I think, is to think about structure forming hierarchically and bigger masses of gas coming together, and they all start settling into the center. But under some conditions, before they settle down and form a big hydrostatic cloud, they might become very self-gravitating and just go crazy and give up all their angular momentum and dump into the center. And there are starting to be some simulations that show that this is in fact what happens. And in fact, you get this nice self-similar isothermal structure. Here's a density profile of R to the -2 developing over time. The gas, as it forms this structure, even though the density profile is not very well defined, is extremely chaotic and very gratifying. From my point of view, it does in fact seem to show that it kind of gets hung up by angular momentum at various points, but then it goes gravitationally unstable and goes in again. This is a bars within bars runaway mechanism that Schmaltz and Frank and I discussed 30 years ago. No, sorry, 20 years ago. Wow. And in fact, the gas becomes very turbulent. And the levels of turbulence that you might get in this sort of infall, and I think this needs to be studied much more by carefully designed numerical experiments, could easily be enough to stop the gas from significantly fragmenting. Some gas might fragment, but a lot of it just keeps going in. What the simulations seem to show is that once this thing gets going, it's very difficult to keep the gas from getting down to really small scales. And by small scales, I mean less than a parsec. So I still think it's plausible that in fact you get mass being dumped into scales of less than a parsec. Okay. If that happens, I'm happy because then I don't have to worry about gravity and n-body dynamics and things like that. I can start doing radiation hydrodynamics, which I feel much more comfortable with. And what you end up with is a supermassive star. It's somewhat different than the kind of star studied by Hoyle and Fowler, who didn't really think about how you would actually form these things. You get a core collapse. The star probably does not lose a lot of mass because matter is being dumped in at an enormous rate. And you end up with a black hole inside a cocoon that has about 100 times to 1,000 times the mass of the black hole. Well, the black hole in that massive envelope is not going to be limited by its own Eddington limit. It's going to accrete at roughly the Eddington limit of the envelope, and that can give you a black hole rapidly getting up to about 10 to the 4 to 10 to the 5 solar masses in less than a million years, probably a few 100,000 years. The kind of structure that this involves is probably something like an enormous radiation pressure supported red giant. As the black hole grows, the red giant gets bigger and bigger because it has to handle more and more energy, more and more luminosity. It gets cooler and cooler, and that has to stop at some point. Because if the gas gets too cool, the opacity drops precipitously. For POP3 opacities, it drops about its 10 temperature to the 13th power. And, of course, you know that even for normal solar abundances, there is a limiting minimum temperature for red giants called the Hayashi track. You cannot match a radiative atmosphere and photosphere onto a convective envelope at a temperature below the Hayashi track temperature. What that does for ordinary red giants is it limits the minimum temperature of the red giant. What it does for a gigantic red giant supported by radiation pressure is it causes the star to disperse because you have one less degree of freedom when radiation pressure is responsible for both the pressure and the energy transport. In an ordinary red giant, you can adjust the density as well as the temperature. Density has no effect on if everything's supported by radiation pressure. Okay, so the quasi-star, which is what we call this red giant, disperses, and you're left with a bare black hole. Okay, final couple of minutes. How do you get from this to the M-sigma relation? You're still 3 or 4 orders of magnitude below the M-sigma relation. Every time this galaxy or proto-galaxy undergoes a major merger, gas is going to be dumped into the center of the galaxy, and if it becomes self-gravitating, it plummets in. It can't plummet at any arbitrary rate. It either doesn't make it at a huge rate, or it goes in at this gravitational, subgravitational rate of about sigma cubed over g. So every time you have a massive merger, you dump incredibly amounts of gas into the center, perhaps, at this very large rate. But now you have a black hole that is bare. It's blown away its original cocoon. Can you reignite its rapid accretion? Well, not clear, but this is what I was thinking about in preparation for this meeting. The envelope mass is less than 100 times the black hole mass. You can't get any kind of static photosphere. You run into this opacity problem. But what can happen is that the gas can try to adjust by carrying away some of the momentum in the outer part of the atmosphere in a wind. And this would, of course, repel the gas that's trying to fall in if you didn't have so much gas trying to fall in. But you have a huge amount of gas falling in, and this gas requires a lot of momentum in order to blow it away. And so you might imagine that there is a kind of feedback, but it's a kind of feedback that occurs down on parsec scales, where the wind that's coming, that this black hole is trying to produce, is trying to push away the incoming gas. And if you balance those two using the same arguments that everybody's used on these kiloparsec scales, you basically get something like the M-sigma relation. Interestingly, the mass of the cocoon is probably bounded from below. It can't be much less than the mass of the black hole, because if it were much less than the mass of the black hole, self-gravitational transport of angular momentum would not operate, and you probably would have trouble getting the gas down to those scales in the first place. So my suggestion is that, in fact, the black hole grows until the mass of the black hole, which is less than the mass of the black hole, which has to be less than both the cocoon mass and this mass, become roughly equal, and that kind of gives you an estimate of when the black hole stops growing. Okay, so is feedback really necessary to explain M-sigma? Well, maybe it is, but if it is, I suspect it's a local rather than a global effect. It occurs down here where the black hole is growing. It's the galaxy that determines the mass of the black hole, so if the galaxy grows by emerging, the black hole will grow, but then stop, not the other way around. The maximum envelope mass is probably close to the final black hole mass, and that may explain why central star clusters in galaxies also seem to satisfy the M-sigma relation. And I think it's kind of neat that there may be some deep connections between the theory of red giant atmospheres and central black hole masses. So just to conclude, I wish I could invite you all to a party at 2311 Hearst. I think this is an example of Dick's calligraphy. Here's another example. That's the famous Goodbye to Burned car party. I'm sure the festivities the same evening will be a reasonable facsimile. And so let me wish Dick a happy birthday.
Time for a couple of questions.
Mitch, there must be an angular momentum issue in the collapse of your massive cloud. Presumably, only a small fraction of the low angular momentum gas will actually form the central black hole. The rest may form a distant fragment.
The idea is that the infalling gas is self-gravitating, so it just keeps forming these non-axisymmetric structures that transport angular momentum very quickly. Where that doesn't happen is after you go, after the radiation is trapped inside the star, probably you lose that effect. And so what I think that happens in that case is that you need some other form of angular momentum transport, and that's what liberates all the energy that supports that puffs up the star. So I am making the assumption that there's some kind of angular momentum transport inside the optical thick region. But outside that, I think gravitation is going to do